Hi everyone, I am Ji Yuan. I am very happy to present my recent work on rotation invariant surface attention-augmented convolution for 3D point cloud classification and segmentation. This work is motivated by the observation that most existing neural networks for point cloud are not rotation invariant. For example, the network may correctly understand and process this aircraft model in a specific pose. But, when the model is rotated, the network cannot properly understand the model in most time, because the network didn't see the rotated pose during the training procedure. To resolve this problem, a remedy is to augmenting the data. That is, different poses of the models are added during training procedure. In this way, the network can see many poses. However, networks trained with simple rotation augmentations cannot generalize well to unseen rotations. A few recent convolutions achieve rotation invariance at the cost of lower accuracies. From this table, we can see that the accuracies of current rotation invariant methods on classification range from 86 to 91, while state-of-the-art non-rotation invariant methods can achieve the accuracy above 93. To address this gap, we propose a novel and effective rotation invariant network. Specifically, we design highly expressive rotation invariant surface properties, which fully describe the local surface structure. Based on these properties, we introduce a novel attention-augmented convolution operator that is agnostic to both point cloud rotations and point orders. We then integrate this operator into a network that can be applied to 3D point cloud classification and segmentation. We conducted extensive experiments demonstrating that our method not only closes the performance gap but also significantly surpasses both rotation invariant and non-rotation invariant state-of-the-art methods across various rotation scenarios. So, in the first step, we design the RISB. For any point cloud input, we extract the sum keypoints, and for each keypoint P, we select k nearest neighbor points. For each neighbor point xi, two adjacent neighbors xi-1 and xi+1 are used to form two triangular local surfaces. Based on this local surfaces, we define 14 rotation invariant attributes including angles and distances describing the surface in Euclidean and tangent space respectively. Please be noted that this is different from previous works using distance and angles. Our RISB is able to completely describe the local surface. Mathematical proof of the completeness can be found in supplementary. Based on RISB, we can now build up the RISurConv. That is, for each neighbor point, we construct the local surface and extract the RISB. Then, we combine them and feed them into MLP layers to learn features. To further improve the effectiveness, this operator is augmented by two self-attention layers as indicated by blue arrows. Based on the RISurConv operator, we can design the network. The classification network comprises 5 RISurConv operators followed by a classifier to output the class labels. The segmentation network follows an encoder-decoder architecture similar to the UNet. To verify the rotation invariance, we conduct experiments under 3 training testing modes, ZZ, SO3 SO3, Z SO3. Here, Z means Z-axis rotation while SO3 means arbitrary rotation. ZZ mode is less challenging because the rotation directions are restricted and in most cases the training and testing poses are similar to some extent while the ZSO3 mode is the most challenging scenario because the training and testing poses differ a lot most of the time. This table shows the classification results on ModelNet 40 dataset. Our method achieves consistent performance across all 3 rotation modes. It is worth noting that our method surpasses both rotation invariant and non-rotation invariant methods. To the best of our knowledge, this is the first work that achieves such high accuracy. It outperforms the state-of-the-art rotation invariant method RISconv++ by 4.7% and outperforms the state-of-the-art non-rotation invariant method point transformer V2 by 1.8% under ZZ case. The same goes with real-world object classification. Our method significantly outperforms the state-of-the-art rotation invariant approach by more than 12%. We also conduct fine-grained object classification which is more challenging because the differences between subcategories are very subtle. Again, our method outperforms the state-of-the-art approaches by large margins for all rotation cases and all the categories. Our method also shows superior performance under the 2 challenging rotation scenarios for segmentation task. This is the qualitative result for part segmentation, showing that our method closely resembles the ground truth. We also conducted a series of ablation studies to further investigate our method in terms of the RISB design, self-attention modules, network efficiency, and the number of local surfaces. That's all. Thank you for the listening. Our codes and pre-trained models can be found at the following link.